When we look at acid-base reactions, we're going to see that many of them are equilibrium processes, particularly ones that involve what are called weak acids or weak bases. But if we take a look at the following two reactions, we've already seen the first one. We saw that ammonia was a base and water was an acid. And we produced ammonium and hydroxide. If we just focus on the reverse reaction, though, if we see what's happening over the course of the reaction, we see that if we're going to go in reverse, the ammonium ion will lose a proton and the hydroxide will accept one. And in this case, the ammonium is our acid and the hydroxide is our base. What do we notice? Well, we see that what was our base in the forward reaction, the ammonia, became the acid in our reverse reaction. So once we made the product of the ammonium, ammonium can act as an acid. And so how do we deal with this? What sort of terminology do we have to explain what's happening here? And we see in the case of the water, in the first reaction, it's an acid. It becomes hydroxide. Hydroxide later, in another reaction, the reverse reaction, is a base. The term we have for these is conjugate pairs. We're going to see that ammonia, if we say it's a base, which we see it as acting as a base in the previous reaction, we're going to say that ammonium is its conjugate acid. So NH3 and NH4 plus form a conjugate pair. One of them is a base, and once it's accepted a proton, it can now function as an acid. So we call these conjugate pairs. And the water has one as well. We saw that the H2O was an acid, and the OH minus is its conjugate base. And if we take a look at our chloride, or HCl, when we first looked at HCl, let's go ahead and let's see if we can get rid of this one. In our HCl reaction, we saw that water was the base in the original reaction. And if we think about the reverse reaction then, if we're thinking H3O plus Cl minus, not a very likely reaction to happen, but if it did, first off, there's no way the chlorine could be an acid because there's no protons on it. So the chloride must be the base, which means that the H3O plus is our acid. Or we can analyze and see, okay, over the course of the reaction, it's lost a proton. So if the water is the base, and H3O plus then must be its conjugate acid. So these are conjugate pairs. Over the course of a reaction, the substance that acts as the base becomes protonated. It can later act as an acid. We call that, therefore, the conjugate acid. We see that these conjugates, in all cases, are only differing by one proton. Your base, the ammonia, has a conjugate acid that is NH4+. While we don't see a reaction of this, if NH3 was an acid, the conjugate base of NH3 would be NH2 minus. Conjugate bases are always one proton less. Conjugate acids are always one proton more than whatever compound you happen to be looking at. And again, this is all a matter of perspective. Whichever one you call the acid, the other one will be the conjugate base. For example, we could say H3O plus is our acid, and water is its conjugate base. So the pairs, you can assign them either way. We could say that H2O is the base and H3O plus is the conjugate acid. It doesn't matter. It doesn't matter which one we're focusing on. The terminology can still apply. So whichever, compound you happen to focus upon, it will have a conjugate base or a conjugate acid or both. In the case of water, water has both a conjugate acid and a conjugate base. H3O plus only has a conjugate base. We don't ever see H4O2 plus. We don't see that. And like the HCl was an acid. Cl minus is the conjugate base. Cl minus has no conjugate base of itself. Cl minus cannot act as an acid. So Cl minus does not have a conjugate base, but it is itself a conjugate base of HCl. So bit of confusing terminology, I'm sure. But the idea here is that if you can analyze in a reaction which one is the acid, which one's the base, we do that by looking at where protons are going, how the protons are being transferred. The one that was your acid in your original reaction becomes its conjugate base. Whatever was your base in the original reaction becomes your conjugate acid. And again, these terms can be moved around depending on where your focus is. If you want to focus on H3O plus as an acid, then water is your conjugate base. If you want to focus as water as a base, then H3O plus is the conjugate acid. All depends on your focus. A conjugate pair, again, only differs by one proton. Let me write that down. If we take a look at something like the sulfuric acid, by the way, sulfuric acid, H2SO4, and sulfate are not conjugates. These are not conjugates. Sulfate is not the conjugate base of sulfuric acid. Conjugates can only differ by one proton. We'll put that with a asterisk here. Conjugate pairs only vary by one H plus. All right, so the conjugate base of sulfuric acid is bisulfate. We have a conjugate here. And the conjugate base of bisulfate is sulfate. So these can be conjugate pairs. They differ by one proton each. But sulfuric acid and sulfate differ by two protons, so they cannot be conjugates. So we have to be very careful when we're looking at things with multiple protons. Same thing with H3O plus versus hydroxide. Hydronium versus hydroxide. Those are not conjugates. H3O plus's conjugate is water. Hydroxide's conjugate is also water. Technically, hydroxide could also have oxide as a conjugate as well. Because we know the oxide ion exists. We don't ever see H4O2 plus. That's something we don't see. But we do see O2 minus. So we could have multiple things going on. But the point is, conjugates only differ by one. And you can identify the pairs pretty easily. Let's look at one more example. Let's say we're putting this with HF. Why not? All right. Let's look at the following. We see we have acetate and hydrofluoric acid coming together. I guess I've revealed which one's the acid because the name is HF, hydrofluoric acid already, producing acetic acid and fluoride. Of course, we should be able to identify HF as the acid. Easiest thing to do is identify the acid because we see it's just losing a proton. HF becomes F minus, lost a proton. This is the conjugate base, the fluoride. Since we already know our acid, the acetate must be our base. And the acetic acid is the conjugate acid. Notice that the acetic acid had, or the conjugate acid had the word acid in its name. Usually pretty easy to tell these things, right? So we have hydrofluoric acid, acetic acid. Those are both acids, right? They're capable of donating protons. Remember, in this sort of definition that we're looking at, it's all about how they are behaving in a reaction at that given time. Acetate is our base. It's becoming acetic acid. Acetic acid is the conjugate acid of acetate. Hydrofluoric acid is our acid, and its conjugate base is fluoride. And again, if we looked at the reverse reaction, acetic acid is now our acid, fluoride is our base, acetate is our conjugate base, and hydrofluoric acid is our conjugate acid. Just terminology. Practice it. Take a look at some reactions, see if you can identify how to name these things or classify them. All right, and so again, it all depends on your focus. If your reaction is written this way, these would be the names you would apply to them. If you write the reverse reaction, the names would be different. You would call acetic acid your acid and acetate your conjugate base. So, with all that in mind, we'll take a look at conjugate pairs, specifically when we're combining them with water. See what will happen there in our next reaction. And through that, we're going to apply the concept of equilibrium.